Thank you very much. I want to thank first for the opportunity to present my research, including some recent results. And as I said, this title is different because I will not only present my published results, but also some recently obtained generalizations. It is, by the way, good that the previous speaker was from Brazil, because we know that dynamics actually starts from pioneering papers by Salas, and this talk is supposed to illustrate also the interplay between dynamics and operator algebras, in particularly Banach algebras. Yes, sorry, just a moment. Yes, okay. Yes, so I will, as we know, Salas started his work by studying dynamics of weighted shifts on ordinary sequence spaces, and very quickly it was generalized by researchers to weighted composition operators, to left multipliers in operator algebras, and so on. And now we will study a very general approach by considering operators that are a composition of an isomorphism and a left multiplier on general Banach algebras. Okay, first I need to introduce some definitions and notation. So for a set S, we let F be a family of subsets of S, and then we consider some families indexed over this S, Tt1, T in S, up to Ttn, T in S, families of bounded linear operators on a Banach space X. And then we will say that these families are disjoint F-semi-transitive, or shortly just DF semi-transitive, if for every collection of non-empty open subsets O V1 up to Vn of X, we can find some element of F, so it is a subset of this SF, which has some special properties. This set F is such that given any t in F, we can find some positive real number lambda t such that this intersection is non-empty. So this lambda t will of course vary on t, but for every t in F, we are supposed to be able to find some positive real lambda t such that this holds. Of course, I should also say, I should have a brief digression. If lambda t we require to be 1 for all t, then actually this definition reduces to something which people from linear dynamics can recognize as Furstenberg disjoint transitivity. So this is supposed to extend the notion of disjoint Furstenberg transitivity and to generalize the notion of disjoint supercyclicity. Disjoint Furstenberg transitivity generalizes the notion of disjoint hypercyclicity, and this notion is supposed to generalize disjoint supercyclicity. And now I want to present the setup, what kind of Banach algebras do we study here. So we let A be a non-unital Banach algebra, and A is the left ideal in some unital normed algebra A1. But for the sake of generality, we will consider two different norms, one norm on A and another norm on A1. And we will say that A satisfies the condition E with respect to A1 if this inequality is satisfied for all A in B in A1, where this one norm is of course the norm on A1, and this is just the norm on A. Also, we shall assume that there exists some subset of A P alpha indexed over some alphas, satisfying that given any open subset O of A and any X in O, we can pick up some P alpha 0 in this set, such that P alpha 0 to the third times X belongs to O as well. So in a way, P alpha to the third should behave like an approximate unit, but in order to avoid speaking about whether the index set is directed or not, I choose to define this condition in this way here. So this condition will be called the condition P. And then what we do is that we take some families of isometric algebra isomorphisms of A1, phi T1, where T runs over S, up to phi Tn, where T runs over S. And we will also assume that phi Tj of A is equal to A, and we will assume that phi Tj restricted to A is also an isometry. So recall in the beginning that A has one norm and A1 has another norm. So with respect to both norms, these families should be isometries and also algebra isomorphisms. Then we will say that this system is disjoint aperiodic with respect, to be more precise, not just disjoint aperiodic, but disjoint aperiodic with respect to this fixed set pi alpha. What does it mean? This means that for each fixed p alpha and every h in F, we should be able to find some subset f of h such that f also belongs to this mathematical f, and such that these relations hold for all RL in 1 up to n, with R different from L, and for all T in F. And finally, we will also assume that for each alpha and all T in S and RL in 1 up to n and all A in A, these inequalities are satisfied. And this condition will be called the condition R throughout the presentation. And then we want to study the dynamics of some operators on this Banach algebra A. How is this operator, these operators defined? So we first take some families, Bt1 where T runs through S up to Btn where T runs through S of elements in A1. And for each T in S and L from 1 up to n, we define the operator TTL from A e to A to be given in this way here for all little a in A. And what is this operator? So it is a composition of this isometric isomorphism and the left multiplication by this element BTL. And now you see that due to the condition E, it is not hard to check that this is a bounded operator, because let us recall the first condition E. It was this condition here, and this ensures that the left multiplication is bounded, and also this is isometry, as we know, so everything works fine, and clearly this is linear operator. And what we want to characterize disjoint F-semi-transitivity of such families, but in order to do this, we need some additional assumptions on these elements BTL. So of course the best case is when BTL is invertible. But we want to study more general case. Later we will see this is because we want to study weighted shifts which are bounded but which are not necessarily invertible. And what can we do to be able to generalize the situation for weighted non-invertible shifts? Well, we can require that for any fixed alpha, BTL has so-called alpha inverse. And we will denote it in this way here. It would mean that for each alpha, there exists an element, this is this alpha inverse, satisfying this equal to AP alpha for every A in A. So recall, observe now that this actually varies on alpha. So it is not a fixed inverse, but for fixed alpha, we require that we can find some element in A1 denoted in this way here, such that these equalities hold for every A in A and for this fixed P alpha. Of course, when BTL is invertible, then all these alpha inverses are simply BTL inverse. But as I said, we want to consider more general case. And once again, since we want to consider more general case when A is not invertible, then we will assume that this is true if and only if A is 0. And this is called the condition C. Okay, so there are several conditions now, but now we are finally ready to present the first result. So under this notation and assumptions, the following statements are equivalent. These families are disjoint F-semi-transitive. Equivalent condition is that for each fixed P alpha and every a positive epsilon, we can find some F in this F, and the families dt where T runs through F, GT1 where T runs through F up to GTN where T runs through F in A. So these families are families in A, such that these inequalities hold, and in addition this inequality holds for all T in F and all RL in 1 up to N. And moreover, we require that for each distinct RL in 1 up to N and all T in F, this inequality holds. And then I should say that, in fact, for example, this assumption of that these families of isometric isomorphisms are disjoint aperiodic, this is needed only for the proof of the implication 1 implies 2, but for the implication 2 implies 1, we do not even need that assumption. But when you see now these equivalent conditions, then of course you can ask, are they easy to check? Because here we require existence of some general families of elements in A. Maybe it is difficult to find such elements, but in fact, thanks to this theory, we can deduce some other conditions, sufficient conditions, which are easier to check directly by calculations. And this is the corollary. So in this case, we let this set S be simply the set of natural numbers, and we let phi be the family of all infinite subsets of N. And then if there exist dense subsets A0, beta 1 up to beta n of A, and a strictly increasing sequence nk of natural numbers, such that for each SL in 1 up to n, every fixed alpha and all x in A0 and is in beta s, this limit is 0 when k goes towards infinity. Now we index over nk instead of t. And moreover, in addition, if for each distinct SL in 1 up to n, this limit is 0 when k goes towards infinity, now again we have nk index instead of t, then these families are DF semi-transitive, and you see again that we indexed over natural numbers and instead of arbitrary set S. So as you can see, these conditions do not involve trying to find out some new families of elements in A, but simply you deal with elements which you already have, and then you can plug in for any x in A0 and is in beta s, and check if this holds. On the other hand, of course, still you have some general dense subsets, but if you can find such dense subsets, then you can check these conditions, and then this will give you, this will be indicator whether these families are DF semi-transitive. Once again, people who work with linear dynamics can recognize this something as disjoint supercyclicity criterion. So it is very similar. And okay, now you can ask me, why are we studying this? So far we are dealing with very general Banach algebras, satisfying several conditions which may seem artificial at the first look, but it will turn out that these conditions are really satisfied in many concrete cases, and in fact I define these conditions out from the concrete cases and not vice versa. So the first case is now the case from my published paper in Philomath, which I put in the abstract for this conference. So now we finally come back to my original abstract for this conference. So for a separable Hilbert space H, we let BH be the space of all bounded linear operators on H, and we let C be the sister algebra of all compact operators on H, of course equipped with the operator norm. And then we can take some orthonormal basis for H indexed over Z, and then for each M in N, we let Pm be the orthogonal projection onto span of these basis vectors from E minus M up to Em. And then we now let L2C be the standard for the convention. We consider it as a right Hilbert module over C. And now this is in fact a Banach algebra. I am not sure whether it is explained in the monographs on Hilbert C-star modules. In the monograph which I have written by Manuilov and Troitsky, I could not find it, but this is straightforward to check. Why is this a Banach algebra? Well, this is because it is a standard Hilbert module, so it is a special module with sequences whose components belong to C, and which are square Sammelbell in the norm of xj star xj converge in the norm in C. Okay, so how do we define multiplication? Well, simply we component-wise define multiplication, but then you have to check whether this new sequence really belongs to L to C, but this is straightforward to check due to these inequalities. Now, of course, these are not number inequalities, but inequalities in the C-star algebra C. So thanks to this, then you can see that this sum is convergent in the norm in C, hence this sequence belongs to L to C. So we are dealing clearly with the non-unital Banach algebra, but of course we should check whether the other conditions which I was speaking earlier are satisfied in this case. So first of all, what should be the left approximate unit? Well, as you can guess, we can define in this way, given any mj in N, we let P tilde jm be an element of L to C, which is defined in this way here. So ith coordinate of this sequence is Pm if I is here and 0 else. And then one can check that in fact it is a left approximate unit for L to C. And then, as I said, since this is a Banach algebra, we simply put now A, B, L to C. But what is A1 in this case? Okay, A1 will consist of all sequences with components in B of H. So not in compact operators, but in B of H, satisfying that these sequences are uniformly bounded in the norm. And then how is now multiplication on A1 defined? Well, easily one can see that it is also defined component-wise. And naturally, what is one norm on A1? It is simply taking the supremums of the norms of Ij, because we require that these sequences are uniformly bounded. And then you can check that this condition E, let us recall once again the condition E in the beginning, it is satisfied in this concrete case. It is easy to check, straightforward. Sorry. And now you see in this concrete example that in fact we have two different norms, one norm on A and another norm on A1. But the condition E is crucial to ensure the boundedness of left multiplication operator. And now, what should be our the families of these isometric isomorphisms? Well, roughly speaking, they should be non-weighted shifts, but not completely non-weighted. We are going to weight these shifts by some unitaries. So then nothing happens in the norm. It is still an isometry, and it is a shift, and it is easily checked that it is a disjoint aperiodic when you consider this family of subsets of n, infinite subsets of n. But let me read it more precisely. Okay. So for a fixed n in n, we can take some natural numbers R1 up to Rn, satisfying these, and then we choose some unitary operators U1 up to Un on H, and for each n in n and S in 1 up to n, we define this map on A1 be given in this way here. So when we apply this map to a sequence belonging to A1, we get another sequence in A1. How is this sequence defined? Well, this what you see here is the jth coordinate. So jth coordinate is I of j minus rsn multiplied from the right by this unitary and from the left by this uniform. So since it is j minus rsn, then you see that this is actually a forward shift rsn coordinates forward, and also it is combined with this another isometric isomorphism corresponding to multiplying by these unitaries. So it is easily checked that this is an isometric isomorphism, but in the special case, when phi is a family of subsets of n which is finitely invariant, this means that for each n in n and every f in f, it holds that this also belongs to f. Then one can check that when you consider this special collection and when you consider this special approximate unit, in this case, these families are indeed form a disjoint aperiodic system. And not only that, but also the condition R is satisfied in this case. What is the condition R? This is the condition R. These inequalities should be satisfied. And finally, we need now to define some these elements B and L in A1. How do we do that? Well, we take some families V and J L sequences when J runs through Z for any natural number n and L in 1 up to n. These are families of operators in B of H that are uniformly bounded in norm. What I mean that the norm of this is uniformly bounded by some constants for all J in Z. And also we assume that each such operator has a bounded inverse. And then for each n in n and in L for L from 1 up to n, we let B and L in A1 be given in this way here. So B and L is now a sequence, and ith coordinate of B and L is simply this operator here. And then, since this operator, each such operator has a bound inverse, then also each such operator is invertible, and then one can check that the condition C is satisfied in this case here. Recall what is the condition C. It requires that BTLA is 0 if and only if A is 0. This is simply checked easily component-wise because this is invertible operator for every I. And finally, we define now T and L in the standard way here. But then you want to ask me whether this B and L has so-called alpha inverse, which I was speaking about. But what is alpha now? Alpha comes from the index set of the approximate unit. And now the approximate unit is indexed over Jm in N2. So our alpha will be the pair Jm. And so we are supposed to find Jm inverse, and it can be calculated. It can be calculated. It is given in this way here. Let me skip reading this, but you can read it from the slide. So we have also this alpha inverse, and now we can characterize df semi-transitivity of these families of operators. Of course, in this special case, when this family phi is the family of subsets of n, which is finitely invariant. And in fact, this reduces somehow it reduces to my published result in Philomath. Still, it is more general because it deals with DF semi-transitivity and not with hypercyclicity. So somehow it is actually gives something regarding disjoint supercyclicity and not hypercyclicity, but yet it is a related result. And I want to read how it is actually in this concrete case. So the equivalent condition is that for every Jm in n, and every epsilon greater than 0, there should exist some f in this f. Recall that this is now the family of subsets of n, which is finitely invariant. So there should exist some f in f, such that for each j in Z satisfying this inequality, we can find these families of compact operators on H satisfying these inequalities, and in addition this inequality for all n in F and all Ls from 1 up to n. And in addition satisfying for each distinct SL from 1 up to n and all n in F this inequality here. And now once again you can say, okay, but here we have some general families of compact operators. Maybe it is difficult to find such families. Do we have some easier indicators for checking this DF semi-transitivity of these families? Yes. In the special case, when F is the family of all infinite subsets of n's, then the sufficient conditions is given in this way. If for each j in Z there exist dense subsets A0j, H1j up to Hnj of H, and a strictly increasing sequence nk of natural numbers, such that for each SL from 1 up to n, and every xj in H0j, and every isj in Hisj, this limit is 0 when k goes towards infinity, and also for each distinct SL in 1 up to n, and every isj in Hsj, we have that this limit is 0 when k goes towards infinity, then these sequences of operators will be the F semi-transitive. So now we avoid, as above, we avoid to trying to figure out some such families of operators satisfying these inequalities, but we can check these inequalities on some dense subsets of H, and this will then work. In particular, I have a concrete example. If you take H to be L2 of R, Lebesgue space L2 of R, and then you can let all these dense subsets be the space of unbounded compactly supported functions on R, and then usually these operators will be some families of weighted composition, weighted translation operators, and then this will work. So there are several concrete examples which can be constructed out of this corollary, and it can be also found in my published paper in Philomel. But we have also some other generalized shifts, which I will not have time to speak in detail, but just to announce, you can also consider this Hilbert module, and then you can consider other kinds of generalized shifts given in this way here, where these are homeomorphisms. Alpha is now homeomorphism of this set omega. So we now consider this commutative sister algebra C0 of omega, and instead of unitary operators, we consider compositions with some homeomorphisms combined with these non-weighted shifts, and that is how we construct these families of isometric isomorphisms. Of course, now our approximate unit is a bit different, and then we also construct some elements B and L in a different way here. Now these are the functions combined with these homeomorphisms, and once again we consider these families, and I just want to give you this corollary, which is given in this way here then for this case here, and one can pass from this even to a more general spaces like this space here, and then also consider generalized weighted shifts on this space here, and thanks to the above theorem, one can deduce this corollary here, which looks in this way here. And here is also some example. I'm sorry for not being able to speak more in detail, but because of the lack of time, but I wanted to focus on this general approach and then just indicate you that there are a bunch of concrete applications which can be deduced from this general approach. And also I want to thank you for the attention. And finally, just to say what are the references. So this is my paper in Philomath. As I said here, I deal only with this concrete case of generalized weighted shifts on the standard Hilbert module of the C-star algebra of compact operators. This general approach, which I presented, will appear now in this archive preprint. It is not published yet. And the other concrete application is a generalization of some results from this paper here. This paper here can also be useful. And this is what I wanted to say. Thank you once again for the attention.